So exponent rules are something that you're going to use literally till the end of your math days. Like I still have people in calculus using these exponent rules. So it's important to learn them and to see where they come from. If you see where they come from, then you remember them a little bit better. So the first thing that they do here is they do expanded, writing these out when you're talking about exponents. So that's why I had you read the first couple pages in your book, because it just basically explained what an exponent is. That's something you should have had in pre-algebra, so you should know what an exponent means. But I just wanted you to review that a little bit with those first two examples. Then we got into the patterns that are created when you start multiplying like bases. So let's talk about what I mean by base. The base is this big number, right? That is on bottom. The exponent is the little tiny number that is on top, and it is basically just repeated multiplication. That's what this is, repeated multiplication. And so this is 2 squared times 2 cubed. And so if we were to write that out expanded, 2 squared is 2 times 2, and then 2 cubed is 2 times 2 times 2. And what you should see here is that you end up with 2 to the 5th, all right? This is what happens when you multiply like bases. So when you did this second one here, 7 to the 4th times 7 to the 1st power, then you should have seen that you had 7 to the 5th power. All right? 7 to the 5th power. What happens when we multiply 3 squared times 3 cubed times 3 to the 1st power? Well, we have 2 3's here. 3 3's here, and then 1 3. How many 3's did I end up with? 6. And then for this last one, I had 6 x's, and then I had 3 x's. How many x's did I end up with? What is the pattern that you saw happening here?
You add the exponents.
Correct. And so that is my rule. That is my rule for like bases. The rule is if I have a to the m times a to the n, that is going to be equal to a to the m plus n. That is your first exponential rule. When you have like bases, you add the exponents. That is the pattern you should have seen when you did this page. All right? For the second page. So for this one, we are dividing, and they want you to do it by expansion. So for the first one, the example they gave you, they had 3 to the 6th. So they had 3 repeated 6 times over 3 to the 4th. And what they used is they used cancellation, just like we would do if we were reducing fractions. They canceled it 1 to 1, all right? And so for this one, we could cancel a 3 to a 3. We could do that 4 times, all right? And how many 3's did you end up with? 2. And so if we do the next one, exactly the way they did it, we have 4 x's on top, 3 x's on bottom. And then what happens when we cancel? Well, we can cancel 3 of each, right? And we're left with how many? 1. And as you did this, what is the pattern that you saw? What started happening to your exponents? You're subtracting them, and that is this rule. If you have a to the m over a to the n, you subtract your exponents. Now keep in mind, you have to have the same base to be able to do this. I could not have 3 squared over 4 cubed and just subtract my exponents. It has to be the same base. All right, but as long as it's the same base, this is the rule. If you are dividing like bases, you subtract their exponents, and this is why, because they cancel out. All right, let's look at the next one. In this particular one, we were taking a power to a power. All right, so we had 4 squared, and they wanted us to cube that. So we took 4 squared, and we did it 3 times. And then we expanded one more time. We expanded those 4 squareds. We have 4 times 4, 4 times 4, 4 times 4. And how many 4's did we end up with? 6 of them. For this next one, we have x cubed times x cubed times x cubed times x cubed 4 times. And then if we expanded that, how many would we end up with? 12. And so as you go along, what is the pattern that you see happening here? What are they doing to those exponents? They are multiplying them. And that is the rule. If I have a to the m and that whole thing is raised to the n, my rule is that I multiply those exponents. I multiply those exponents. Question. All right. Now for this one, it looks like it's the same thing. All right. It looks like it is the same thing. My rule here, so if I were just going to use my quotient rule, I am just going to subtract them, right? And so I subtract this and I get 3 minus 5. Well, 3 minus 5 is a negative 2. Okay? So let's see what happens in expansion. Well, I put my 3 5s on top, my 5 5s on bottom. When I cancel them out, I am left with 2 5s, but where are they? They're on the bottom. They're in the denominator. So as you start to see this pattern, 2 minus 6 for this one right here, well, that should be negative 4. When I do this out, then, and I start my cancellation, I have a 1 on top. Because remember, something divided by itself is 1. So when you have only something left in the denominator, you need to put a 1 in the numerator. And so you're left with 1 over these 4 x's. And the way you write that is x to the 4th. And so this is kind of a different rule. This rule tells you that a negative exponent will move it. Okay? A negative exponent will actually reciprocate your positive exponent. That's basically what it does. So my rule here says if I have a to the negative m, all right, a to the negative m, that is the same thing as 1 over a to the positive m, okay? So the negative just moves it. It moves it from your numerator position and it puts it in the denominator. And as we get further along with these rules, it can do the opposite as well. If you have a negative in the denominator, it can actually bump it up to the numerator because it actually reciprocates that number. It means 1 over it, 1 over. And so this is the rule that you should have seen with negative exponents. Negative exponents move it to the denominator. They move it to the denominator. All right? Questions on the negative exponent. Negative exponent. All right? The rule that we looked at here was 0. So for this one, we had 2 minus 2. Well, 2 minus 2 is 0. So I have 5 to the 0 power. That does not mean 5 times 0. So this answer is not 0, okay? What this means is 5 to the 0 power. And so what does it mean if we expand it? It had 5 squared, so I have 2 5s over 2 5s. Well, I can reduce it. 5 divided by 5, that becomes 1 over 1, right? 5 divided by 5, well, that becomes 1 over 1. So on the top here, I have 1 times 1, which gives me 1, and 1 times 1, which gives me 1. And the way they did it is they just multiplied. 5 times 5 is 25. 5 times 5 is 25. If you reduce at the end, you also get 1 over 1. And so your answer is 1. And so as you did this, you should have gotten 1 for every single one of those answers. Because this rule is anything to the 0 power is in fact 1. How many times can you take that to the 0 power? Anything to the 0 power is 1. All right?